Hey everyone, today I'm going to discuss Compton scattering. So previously in the videos about photoelectric effect, I discussed that the photoelectric effect was proof that light was a particle, and Compton scattering is another proof that light is a particle. Alright, so I'm going to just describe how the Compton scattering experiment first. So I just drew this line, this axis, just to make everything easier to look at. So scientists would put an electron at rest somewhere, and they would shine a light of known wavelength onto the photon. And eventually the light's going to travel, and then it's going to collide with the electron. And scientists observed that when the electron and the light collided, both electron and light was scattered by this angle, these angles you see here. And the electron gained velocity, meaning that the electron has now an increased kinetic energy. And also another interesting thing that scientists observed was that when they measured the wavelength of this scattered light over here, and let's call this wavelength prime, they found out that the wavelength had actually increased. And we know that frequency is speed of light divided by wavelength. So if wavelength increases, then frequency would decrease. And since we know that E is hf, where h is Planck's constant and f is frequency, we know that the energy of light has decreased. So in simple words, energy of light has decreased and the energy of electrons has increased. Now, what does this diagram look like to you? To me and a lot of other scientists, when they first saw the Compton scattering effect, it reminded them of a 2D collision of. It looked like a collision diagram of two particles. And these kind of collision effects are only possible. We firstly proved that there was a collision between the photon and the electron by the transfer of energy. And this kind of collision effect is only observed under the basis that light is a particle. So through the Compton scattering, we have effectively proved that light is in fact a particle. And in the formula booklet, there's actually a formula which states that the change in wavelength is equal to Planck's constant. Oh, you know what? You can just read this. This is the equation that you have to use. I will not derive it because I don't know how to. And it requires some relativity, but this is all on the formula booklet, so you don't need to worry about memorizing it. But one key detail that might come up in exams is that this number, the difference in wavelength, is going to be very, 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 very tiny. So in order to observe this effect, this Compton scattering effect, you would need to choose a wavelength of light that is somewhat comparable to this difference of wavelengths. And so, which means you need to observe Compton scattering, you can't use a high wavelength light like visible light. You have to use a very high energy photon with high frequency, very low wavelength, for example, like X-rays and gamma rays, to observe this phenomenon. So keep that in mind.